Swayam Prabha. Digital India. Educated India.
Welcome to the first lecture of Module 3. Module 3 is basically on Introduction to the Liquid Additive Manufacturing. In today's lecture, we shall discuss about the classification of liquid additive manufacturing, and then we shall start our discussion on photopolymerization based liquid additive manufacturing process. There are two types of liquid additive manufacturing processes. First is called as photopolymerization based process and another is called as rapid freezing. Our first target will be photopolymerization based additive manufacturing process, and today we shall discuss its working principle and its subsystems. And then based on the subsystems, we shall classify the photopolymerization based additive manufacturing process further. So, if you recall the classification given by ASTM, the additive manufacturing is categorized into 7 categories. First is wet photopolymerization, then material jetting, binder jetting, material extrusion, sheet lamination, powder bed fusion and directed energy deposition. The classification here is reproduced again, and it can be noticed that the wet photopolymerization and material jetting uses liquid form of the raw stock material. As the name suggests, a liquid based additive manufacturing process uses a liquid form of raw material. There are different manufacturing routes in this broader classification of the additive manufacturing. Therefore, in this course, liquid additive manufacturing processes are further classified into 2 categories. First, photopolymerization and second, rapid freezing. If we look into the classification given by us, which is based on the raw stock material, which is the additive manufacturing process, those uses liquid, solid or gas. If liquid is the raw material, this is going to be our focus. Now, the first one is photopolymer based process and another is rapid freezing based process. Let us first discuss about the photopolymerization based processes. The photopolymerization based liquid additive manufacturing processes uses UV light. When this UV light falls onto a photocurable resin, it starts hardening. After some time, it forms a solid body and that can be used as a product or prototype. The photopolymerization based liquid additive manufacturing processes basically build objects by photocurable liquid resin that cures or hardens under the exposure to the UV light. The UV light scans the cross section of each slice to selectively curing it, and after completing the curing of a layer, the build platform is pulled down or up and the next layer of the liquid resin spreads over or below the previous layer and similarly got cured. The whole object is built by repeating these steps, and finally the uncured liquid drained out from the wet and the object proceeds for further processing. Typically, a wet photopolymer resin is consisted of two material. First is called as photoinitiator and second is called as monomer. Photoinitiator here represented by Pi and the monomer is represented by M. When the UV light falls onto this resin, the photoinitiator absorbs the energy from the UV light, that is in the form of H nu, and produce the free radicals. This happened because the photoinitiators got excited when absorb the energy H nu from the laser and produce the free radicals. As you can see, Here as you can see, these red dots are available now. These are nothing but the free radicals. Then after that, the photoinitiators, those are having the free radicals with them, start transferring these free radicals with the monomers and hence form a bond, as you are seeing here. This chain keeps on transferring the photoinitiator with the neighbor monomer, and the chain keeps on propagating. The phenomena of propagating the chain is called as chain propagation, and when the first bond is formed, the process is called as chain initiation. It keeps on happening and the chain got terminated when the free radicals available with one monomer and the free radical available with another monomer form a bond together, and hence this particular chain is now formed and it got terminated also because there are no free radicals further available with this chain. Like this, there are several chains got formed and hence the liquid resin got hardened. So I have with me some photopolymer liquid resin, as you can see here. We shall try to give you a demonstration of hardening this liquid photopolymer resin here itself. So what we need some liquid photopolymer and we need UV light. So I have got a UV light also here. If the UV light will fall onto this liquid resin, the photoinitiator will start absorbing the energy and will provide the free radicals. As already discussed, these free radicals then will transfer to the monomer and will start forming the bond. The chain will get propagated when the free radicals will not be available in a chain and form a separate bond. So let us first spread some amount of photopolymer resin on this substrate and then we will expose that particular layer with the UV light. Based on the power of the UV laser which we are using, the time will be taken appropriately. If the power is high, of course, it will take less time to cure the photopolymer resin. If the power is less, it will take more time obviously. So after some time, we can see that the liquid photopolymer which we spread over this has been cured, and we can see that it is now available in the form of a layer. The same process you can repeat for each and every layer and build the part. The only thing you have to be careful about is the portion you are curing should be within the material and the portion in the slice which is outside the material should remain in the liquid form. So this is the basic principle of the wet photopolymerization based liquid additive manufacturing process. So as you have seen how the liquid photopolymer got hardened after we expose it to UV light. The principle remains same and we need to just now build a system which can appropriately give the relative motion between this UV light and the photopolymer or some other means so that we can just cure the required region in a layer and the remaining region should remain in the liquid form itself. Therefore, let us now discuss what are the different subsystems are required if you want to develop a 3D printer or additive manufacturing equipment based on this principle. So, of course, you will first need the photopolymer liquid, then of course, you will need a UV light, then there should be some scanning system. This scanning system is particularly required to cure the region where the material is and keep the region in the liquid form where there is no material in the part. For example, this is the contour we have obtained in a slice. We know that in this region there will be material, hence the UV light will fall onto only on this region, while in this region UV light should not fall. Hence, this particular region will become hard or solid, while this particular region will still remain in the liquid form. We can repeat the process and build the entire part in this way. There could be different scanning systems. The next important subsystem of the equipment is the build direction. Like in which direction we are building the component. Either we are building it in this manner, like in plus Z direction, or we are building it in upside down manner, like this. Hence, the growth is downward in minus Z direction, or we are building it in any random direction, then it will be variable direction. The fifth very important subsystem in such additive manufacturing machine is the recoating system. Means how you are going to spread the next layer over the substrate or the pre-built layer. This particular system is very critical because this is the system which is going to define the accuracy of the part you are going to produce on the machine. If you are able to spread a layer of very less thickness, then of course the accuracy you produce in your part will be very good. A typical part produced on such a machine is here. One of the very important benefit of photopolymerization based additive manufacturing processes is that we can produce the transparent objects. Like you can see here in this particular object, the internal channels are visible. This particular object has some internal channels inside, those are quite visible because the part is transparent. Also, it can be observed that the surface roughness we are producing on this particular part is phenomenally very good. It is because the layer thickness which we typically able to produce in the photopolymerization based processes is around 5 micron. Therefore, we can say that these processes are among the most accurate additive manufacturing processes. Let us now discuss in detail the different types of options available for each of the subsystems we discussed. The first one is the scanning system. There are typically 5 types of scanning systems are available in wet photopolymerization machines. The first one is called as galvanometer, second is called as flying liquid, third is called as flying optics, and fourth is called as DLP, and the last one is called as mask. What is galvanometer? So, galvanometer is nothing but arrangement of two mirrors orthogonal to each other. As you can see, this is mirror 1 and this is mirror 2. A laser beam is coming from here. When it strikes on the mirror, it got deflected and it falls onto the another mirror. Again, it strikes on this mirror and fall down onto the bed or another lens for correction in between if required. As you can see, if I rotate this particular mirror by some angle, then of course I will be able to deflect my beam at another location on the second mirror, and as a result the spot on top of the liquid bed will be able to also move. In a similar fashion, if this mirror also rotates, the spot will be able to move in another direction on the bed. This typical system is called as galvanometer. Why do we use galvanometer? It is because the mass of the mirrors are very less, and hence if you want to deflect the laser beam, you can deflect your mirrors with a very high speed because the mass of the mirrors are very less, and hence as a result the laser beam can move with a very high speed on the top of the liquid bed. However, there are some issues, like when the beam strikes at an angle on the bed of the liquid photopolymer, the spot may not remain circular. For that, sometimes the f theta lenses are used. We shall discuss in detail about how this galvanometer works when we shall discuss about a machine which particularly uses the galvanometer. Next option for the scanning system is flying liquid. In the case of flying liquid, the laser source remains stationary and the liquid bed moves in x and y direction. That is why we are saying flying liquid, because right now we have xy motion with the bed. It is very similar like I did here. I was moving the substrate back and forth when the light was stationary. If I move the laser beam or the UV light source, then it will be called as flying optics. As you can see in this diagram, this is the laser which is coming from the bottom side, and there is a transparent window and some liquid is available here. This is nothing but the liquid photopolymer. When the laser falls onto it, the portion may got cured. Now this optics of the laser is mounted on the XY table, and hence the optics itself can move in X or Y direction. Therefore, it is called as flying optics, because now we have given some XY motion to the optics. Next is DLP. Digital light processing, or DLP, is nothing but the array of mirrors. It is very commonly available in your projector also. A macro scale version of the same we have also developed for demonstration, as you can see here. This is a typical example of a DLP. As you can see, there are a lot of mirrors arranged here. When the light will fall onto these mirrors, it will get deflected, and hence wherever it will get deflected, if the liquid resin is available at this location, the liquid resin will get hardened. Now assume that if each of these mirrors are attached with some electromagnetic coil, and we are giving appropriate potential difference to that particular coil, then it may happen that these mirrors may move along a hinge like this. Now you can see, if the mirror is moved at this location, that means it will deflect the light here, and if the liquid material is available at this portion, the light will not go onto the liquid material. In that way, you can appropriately scan the region where the material is, and the region where there is no material, the light will get deflected somewhere else. So in this model, we have also tried to develop these mirrors, and these mirrors are attached with tiny steel plates at the back side. If I give some magnetic field to these, then these mirrors will deflect along its hinge point. I have a permanent magnet in my hand, and if I move it on the back side, you can see that I am able to deflect these mirrors. The work I am doing here by the permanent magnet, in the real life this thing is done by the electromagnetic coils, and appropriately I just give the input. Like for example, I want to activate this mirror and deactivate this mirror, so I will give 1 0. Appropriately I can give 1 0 1 0 1 0 in an array, and hence the appropriate mirror will deflect the light at the particular location, and if the material is not there, it will deflect it somewhere else. So this is called as DLP. Next is the mask. As you can see, if we want to scan, for example, this particular layer, and the material is available here, what we can do, we can develop a mask on which there will be opaque material available here. This is for example the opaque material, and there will be a transparent material available here in this zone, and again some opaque material will be here. So basically a negative of the slicing data will be produced on the mask, and when a floodlight of UV will fall, we will just put that mask under this so that the light can pass through only from the appropriate region, and in the region where the light is not required, it will get blocked. These type of masks can be created instantaneously, or one can fabricate this mask in the beginning itself as a pre-processing. If it is instantaneous mask, then of course the ink available here can be removed if required, and we can appropriately provide the ink at the region where we do not want the light to get passed. So these are the 5 most popular scanning systems for photopolymer based liquid additive manufacturing. The schematic of DLP and mask are given here again. For example, like I have already explained, this is the UV light which is coming in flood, like it is not the sharp beam, and when it falls onto the array of mirror, the appropriate mirror deflects the light on the top table, and if it is not required, the mirror will deflect the light somewhere else. This is an example of the mask. Here you can see this black color zone is for the opaque portion and the white color portion is for the transparent portion. The light will pass only through the transparent portion and opaque will block the light, and as a result the light will get projected on the bottom, and hence your part will get cured only from the appropriate region and the remaining portion will be liquid. Also, the light which we used for the photopolymer material, the UV light, it could be either as a sharp laser beam or it also can be like a floodlight. This is an example of the floodlight where the light is available everywhere on the area, or the light could be in the form of laser beam. Laser beam is very similar like this projector, like this pointer. Here you can see it is a beam and the laser is available at the spot, it is not available on the entire area. So like I said, the light can be either just like a beam, it will be an example of the laser beam, or the light source can give us the light in a projected area, in the entire area. So this is an example of floodlight. Also, the photopolymer liquid could be either in the form of a wet or it can be in the form of a jet. Meaning to say, the liquid material can be available in a big tank like this. For example, this is the tank and the liquid material is filled in it. Now from the top you are scanning the appropriately and hence curing the part. Or the liquid material may fall from the top like a jet. If it falls like this, then according to ASTM, the technology may be called as material jetting, because we are injecting the material on the substrate. Yes, of course, in that simultaneously the UV light also comes from the back and immediately cure it. The next very important subsystem in the liquid additive manufacturing machine is the build direction. The platform available for building the part can build it in Z direction. In that case, for example, this is the build platform, it will be attached with some mechanism, for example, a scissor lift. And when this particular portion will move, it will go down. As it will go down, from the top laser is coming and falling into it, it will keep on building the part in the top direction like this. This will go down and it will keep on building the part. Hence the growth of the part is in plus Z direction. Also, you can assume that the build platform is upside down. It is something like this. Now if I move it, this particular portion will go in this direction, and from the bottom assume that there is a laser light is coming. Hence the part will be built like this. This is the first layer, then again it will go up, and again next layer will build like this. So growth will be in this direction, and this is called as minus Z build direction. It could be the variable direction as well. In the case of variable direction, I can attach my optics on a robotic arm, for example. For example, this is your laser light and there is a liquid tank here. Now I can move my robotic arm, I can put it inside the liquid tank and keep on changing its direction. As a result, the part we are building may also keep on changing its build direction. This is called as variable direction. Next, like I already mentioned, the subsystem will be a recoating system. This is going to be the very important system of the additive manufacturing machine, particularly for liquid additive manufacturing, as this will decide what should be the layer thickness of the part which we are going to build. The first one is called as deep dipping. In the case of deep dipping, after realizing a layer, the entire part goes down and the liquid material available in the tank flows over it. So we are dipping the part deep into the tank. Then we of course lift it up and remove the excess material by a recoater, or sometimes called as doctor blade, and creates a thin layer of the liquid photopolymer. This process is called as deep dipping. Another subsystem is called as top feeding. In the case of top feeding, we have a hopper here and there is a small slit in the hopper. As the liquid photopolymer is feed here, the photopolymer falls like a curtain, and as this thing moves forward, it spreads the layer on the bottom side. Hence we are feeding the material from the top side. That is why it is called as top feeding. Next one is the bottom feeding. Bottom feeding is usually preferred when the part is built in minus Z direction. As a result, the liquid is fed from the bottom side, not from the top side. And usually this feeding is performed under the gravity only. No additional system is used for feeding the material. We shall discuss about this system in detail when we will discuss about this, when we will discuss about a machine which is particularly uses this particular technology. So these are the three most popular recoating systems in the wet photopolymer based liquid additive manufacturing. Now let me put all these subsystems together. Like I have already mentioned, for the scanning 5 systems are available: galvanometer, flying liquid, flying optics, DLP and mask. Then the shape of UV light could be laser beam, already you have seen, or it could be the floodlight. Also the shape of liquid could be a liquid wet like a big tank, or it could be liquid jet. Also the build direction could be in plus Z direction, in minus Z direction, or it could be a variable direction like the optics when it is attached with the robotic arm. And the last one is recoating system. It could be deep dipping, top feeding or bottom feeding. Now if you pick any commercially available additive manufacturing machine, you will be able to find out a subsystem here, and you can connect the thread between the different subsystems, and hence a particular machine will be available. Now let me just show you the different types of machines available in the market. Like the system which uses galvanometer for scanning, it uses shape of UV light as laser beam, shape of liquid is nothing but liquid wet, build direction is in plus Z direction, and recoat or spread the new layer by deep dipping technique. This particular machine was developed by 3D Systems and it is called as SLA. That was the first known additive manufacturing process. It was developed in 1980s and they uses these subsystems. Then after that this green color line, it shows that a next version of the machine which was developed by 3D system itself, again after few years. The only difference was in the feeding mechanism. Rest of the system, the scanning system was same, shape of UV light was same, shape of liquid was same, build direction was same, but instead of using deep tipping for recoating the layer, they developed a technology for top feeding and they call it as Zephyr. In a similar fashion, other machines are highlighted here and the subsystems used in these machines are connected through a ribbon here. This particular classification cleared lot of your doubts related to the additive manufacturing systems. Not only that, if you want to develop your own new machines which was never explored before, you can explore from here. For example, galvanometer with laser beam but with liquid jet, there is no such machine, there is no ribbon connecting like this which is using galvanometer, laser beam and liquid jet. But if you want to develop such a machine, you can think about it. Let me summarize. All the systems available are highlighted here. The red color line shows the system of 3D systems SLA. The main 5 subsystems available in the 3D systems SLA can be tracked here by tracking this red line. Then 3D systems SLA, which uses Zephyr as a technology, is shown here in the green color ribbon, this particular ribbon. And then this black color ribbon shows the microstereolithography. It uses flying liquid. Then object polyjet, which uses flying liquid as well as flying optics, both together, this blue line, and utilizes the floodlight and liquid jet, build the part in plus Z direction and provide the material by top feeding. Next is Auto Starts E-Dart. It is highlighted here in orange color. It uses flying optics, utilizes a laser beam, uses a liquid wet and build the part in minus Z direction, in upside down direction, and utilizes the bottom feeding. As I have already mentioned, when the part is built in minus Z direction, usually the bottom feeding is preferred. Next is the Perfectry Akula. It uses DLP technology and utilizes the floodlight. It can be tracked by the yellow line. Uses the liquid wet, build the part in minus Z direction and provides the bottom feeding. Next is Solid Ground Curing. It uses mask for the scanning system and then uses the floodlight and utilizes the liquid wet, build the part in the plus Z direction and provides the top feeding. It can be tracked by this line. And the last one is robotic SLA, which can use the flying optics and a laser beam. It can go inside the liquid wet tank and hence a liquid wet, and also it can build the part in variable direction, and further the feeding can be done from the top. So this is how our classification can nicely accommodate all the commercially available liquid additive manufacturing systems. In this course now, we shall discuss each and every of these processes in detail in the subsequent lectures. With this, thank you very much.